Welcome to Session 9.0, Food Preparation. This EMSI training section covers energy basics on food preparation. Your presenter is Rick Mitchell. Food preparation in the residential, business, and commercial sectors. Food is a part of life, and for many, food preparation is a major part of their business. Residentially, food preparation often involves the use of small appliances which consume relatively little energy. But for commercial food outlets, larger appliances can contribute heavily to the overall power consumption. Areas which are involved in food preparation are not solely restricted to restaurants and fast food outlets, and can include function centres, clubs and community centres, hospitals, nursing homes and other care facilities, and not-for-profit kitchens and food charities. Food preparation technologies. There are a great number and variety of appliances used in the area of food preparation. Loosely, the more common of these can be identified as fitting into one of four categories: ovens, cooking surfaces, small appliances, or extraction. Within this largely user-driven sector, many of the reductions in energy consumption will come from consumer behavior changes as well as efficient appliances. Ovens include the more familiar or conventional oven technologies, as well as more modern contributions such as steam ovens and convection ovens. Cooking surfaces almost specifically refer to cooktops, but are inclusive of deep fryers, industrial griddles, and the likes. Appliances covers goods from the scale of a toaster to the industrial mixers used in bakeries. And finally, exhaust hoods are frequently employed to aid in food preparation process. Achieving energy efficiency in ovens. When faced with an oven in an audit situation, it is important to understand how to calculate the energy use represented by the system. Here we start again with the base calculation. Annual kilowatt hours is equal to the calculated power divided by the efficiency of the system multiplied by the time for which the system is run per annum. As energy efficiency is essentially a product of reducing the total kilowatts of a system, it can be achieved through either reducing the power, increasing the system efficiency, or decreasing the time of use. In this instance, information regarding the rated power consumption of an oven is often available on data tags found on the side or back of units. Further information can also be found on the MEPS label for MEPS rated products, or likewise for Energy Star rated products. Often people in newer premises will also keep the product manual, which comes with the oven, and this can be a great source of information. If this is unavailable, a simple Google search of the model number often yields fruitful results. System efficiency is affected by a number of factors, namely the type and age of the appliance in question, the quality of its component parts and construction, the frequency and quality to which it is maintained, and the frequency of its use. Firstly, to reduce the power consumption of the appliance, it must be understood that rated power is directly related to the way in which energy is converted into heat energy, the efficiency with which this is done, and the power required to accomplish this. Generally, the first consideration is the efficiency of gas ovens, as compared to that of electric ovens. Electric ovens are popular for a number of reasons. Firstly, they heat up quickly, making them ready for cooking faster and reducing the need to waste energy in preheating. Electric ovens are also multifunction, allowing you to perform a number of different processes. They tend to have a top and bottom element, a grill, and sometimes a fan, which allows the user to customize the oven's operation to suit the foods which are being prepared. Electric ovens are also generally cheaper to buy, which is a consideration if your client is on a budget. Their cost effectiveness can also mean that you get more in terms of function and size for the same amount of money. However, the price of electricity can mean that electric ovens are expensive to operate over the life of the oven. Gas ovens offer precise temperature control and heat up very quickly once turned on. If the temperature needs to be raised or lowered during cooking, the actual temperature inside the oven will adjust very quickly, unlike electric ovens which need time to raise or lower their temperature. Something to consider with gas ovens is if they have electronic controls or an electric grill, they will still need to be wired into the electricity supply. Ventilation of gas ovens is more important than in electric models, as carbon monoxide, a toxic gas, may be produced by the burning of gases. The additional energy used in this process means that gas ovens are generally more energy intensive than electric ovens, which require significantly less ventilation. To illustrate the difference, A brick test is a test in which a chilled, wet brick at 5 degrees Celsius is placed into an oven where its temperature is raised to 60 degrees Celsius. The time and energy which is required to achieve this is recorded and compared across a number of similar ovens. Results show that gas ovens consume more on-site energy than the electric ones, largely due to the requirement of extra ventilation for safety reasons causing more heat loss. In addressing energy consumption relevant to food preparation, it is key to address what it is that is being prepared, and the most efficient way to prepare it. In many instances, smaller or alternate oven technologies may produce better results for less energy. There is an increasing trend being seen in the use of convection and microwave ovens, and steamer ovens which use less power than conventional ovens. Conventional ovens rely on radiant heat and hot air to cook food, however the highest temperatures are found towards the top of the oven. This can cause uneven cooking of the food as the air is not circulated and therefore the temperature is not constant throughout. Conventional ovens take longer to cook and require a higher temperature to cook food than convection ovens, making them less energy efficient. There is also a slower response time when changing temperature. Convection ovens, put simply, are just conventional ovens with a fan that circulates the air around the oven. An extra heating element is added to the back to keep the air temperature constant. Commercially, these ovens are much preferred over conventional ovens for their excellent cooking quality, faster cooking times, and energy efficiency. By cooking at a lower temperature for a shorter time period, these ovens save plenty of energy that would otherwise be spent using a conventional oven. They cook food evenly and to a better quality. Many ovens today can operate in both conventional and convection modes by turning the fan on and off. This allows greater cooking flexibility, giving the option to brown the top of the food a little more with a top heating grill, for example. Also keep in mind that many ovens today will have electric controls and starters regardless of whether they are heated using electricity or gas. This means that they will use standby power. Microwave ovens are a more energy efficient way of cooking. They emit microwaves that cause the water molecules to vibrate and subsequently heat up. The quality of cooking in microwaves is usually not as good as convection ovens, however they are great at heating food or drinks quickly, often without heating the container. Some behavioral recommendations to reduce the energy consumption of microwave ovens include switching the device off overnight to reduce standby energy use, and remembering to remove food from the freezer before it is required, allowing time for the food to thaw naturally to room temperature before heating. The three major models of steam ovens are convection, pressure, and connectionless. Steam has a huge heat transfer potential, making it ideal for cooking. When the water turns into steam, it undergoes a physical transition known as phase change and absorbs a large amount of heat energy as it makes the transition. Then, when the steam condenses back into water in the oven, the additional heat energy is transferred directly to the food. Steam ovens offer benefits to users such as fast cooking times as well as the retention of vitamins, nutrients, flavor, color, and texture of the ingredients. A steam oven can cook just about anything, however it doesn't brown or crisp food. This is because it cooks with moisture rather than hot elements. Combination steam ovens are very popular in commercial kitchens and are becoming increasingly popular for domestic use. They use either electricity or gas as well as a steamer so that food can be cooked thoroughly and quickly with the steamer, then browned or crisped in the convectional mode. Losses in the system can significantly increase the power required to heat, and therefore cook foods. Factors such as heat retention, efficient ventilation systems, and excess air reduction can all contribute to the efficient performance of a unit. This table, sourced from the EU's Rev02 study, illustrates a number of possible or suggested improvements and their effect on the efficiency of an electric oven. It should be noted, though, that in practice it is unlikely that measures of this nature would be taken due to the costs incurred for savings which are seen to be minimal. Here, a table taken from the same document illustrates the effects of possible initiatives implemented on a gas oven. Again, it is highly unlikely that these reflect practical solutions to improving the energy efficiency of an oven. Sourced from the European Committee of Domestic Equipment Manufacturers, this table similarly makes suggestion for improving the efficiency of microwave ovens. A number of these, such as removing clock displays or implementing mechanical controls, are commonly in use today. Achieving energy efficiency in cooking surfaces. For the purposes of calculating energy efficiency, cooking surfaces, namely hot plates, burners, griddles, and fryers, work on the same principles as ovens. That is, the real power is a measure of the rated power divided by the efficiency of the appliance. Like ovens, the power consumption of cooking surfaces is directly related to the way in which the energy is converted into heat energy, the efficiency with which this is done, and the power required to accomplish this. Here we make the same choices between gas and electric. There are three types of electric hot plates: coil, solid, and ceramic. There are also three different types of ceramic hot plate: standard, halogen, and induction. Radiant coil hot plates respond rapidly and are easy to adjust. They are the cheapest electric hot plate on the market and are more efficient than solid and ceramic standard and halogen hot plates. They can usually hinge up to allow for easier cleaning. Solid electric hot plates are fixed to the hob, which allows for easy cleaning. They are less efficient and have a slower response time than coil hot plates. Due to the fact that they retain heat longer than coil plates, they can be switched off prior to finishing cooking in order to save energy. Auto-sensing elements will assist with temperature control, and sintered elements give faster cooking times. One thing to keep in mind is that they need to be regularly cleaned to maintain their efficiency. Ceramic halogen and ceramic standard cooktops have the advantage of looking more stylish and being easier to clean than the coil and solid hot plates. However, they are less energy efficient, have slower response times, and are more expensive than coil and solid hot plates. With the introduction of induction cooktops, these hot plates have become somewhat less popular. Ceramic induction cooktops use electromagnetic principles to heat the pot directly so that the ceramic only heats up due to conduction of the heat from the pot. This means that if the cooktop is accidentally turned on, it will not heat up unless the right pot is on the stove. Most units will automatically switch off after a certain period if an iron-based pot is not sensed on the element. The flat glass surface gives the induction cooktop a stylish look and makes it easy to clean. Advantages also include very fast cooking, immediate response, and precise temperature control. Disadvantages include a higher cost both in the expense of the cooktop and the need for special cookware with iron bases. The table here shows the average efficiency of these hot plates. Induction hot plates at 80 to 85% efficiency are significantly more efficient than standard, halogen, solid, and coil models. Gas burner cooktops provide rapid response, easy adjustment, and good temperature control. Gas consumption will vary with the size of the burner and the setting that is used. New models have electric starters, but many old units can have gas pilot lights, which can account for 40% of the energy use of the stove. Here, more so than in ovens, the efficiency of the unit is closely tied with its ability to transfer heat into the cooking service and subsequently the food itself. The more the heat is able to reach the food, the more effective the cooking process will be. And a more effective cooking process means a faster process, which in turn means less energy is required. To achieve this, ensure that correctly sized pans are being used, hot plates are not being set to unnecessary temperatures, foods are completely defrosted, naturally, before being cooked. Where possible, lids are used to speed up the cooking process, and meals are cooked using the minimum number of pans necessary. As with the operation of any appliance, efficiency is dependent on the hot plate, fryer, or griddle operating at its maximum capability, with as little heat or energy loss as possible. The proper running of such an appliance is reliant on maintaining and repairing the appliance, and recalibrating the appliance if necessary. Though relatively minor by themselves, the cumulative effects of wear on appliances can significantly reduce the operating efficiency. Appliances should be checked regularly for splits or gaps in seals, weak hinges, cracks or damage that may result in loss of heat or leakage, leaking gaskets, damage to any electrical components, clogged burners, or any other such wear and tear. It's likely that over time the performance of kitchen appliances will degrade. Thermostats and control systems can fail or fall out of calibration. Recalibrating thermostats is necessary to ensure that ovens, cooking surfaces, and appliances are operating at the specified temperatures. Replacing or repairing broken elements such as knobs or control panels will aid in the proper use of electrical devices. Achieving energy efficiency in appliances. Generally, appliances used in the preparation of foods are such that any consideration of the efficiency with which they run is negligible. For this purpose, it can be assumed that the rated power is equal to the real power consumption. In any instance where an appliance is likely to work notable under its potential efficiency, this number can simply be divided by the percentage efficiency as in the previous examples. Information regarding the rated power consumption of appliances is often available on data tags found on the side or back of the product. Further information can also be found on the MEPS label for MEPS rated products or similarly for Energy Star products. Generally, the relative cost and scale of implementation would suggest that any reduction in the power usage of a device would be a result of replacing inefficient technologies with more efficient appliances. Reducing or eliminating the number of appliances left on standby can also contribute significantly to the reduction of energy related to food preparation. To accurately reflect the total annual power use of an appliance, one must consider the power used while in standby mode. Standby power is energy used by an electrical device while connected to power but not in operation. There are two commonly identified standby modes. Passive standby is where the appliance is in its lowest power consuming mode and can be detected by an LED light, clock, or where the device is waiting to be switched on by remote. Active standby is where the appliance is on but not performing its main function. A device is usually only completely off when it's switched off at the wall, as devices can still consume very small amounts of power even when they are switched off at the device's power switch if it has one. To calculate the total energy consumed annually, simply multiply the real power of the appliance when in use, in kilowatts, by the number of hours it is active per annum, and add it to the real power of the appliance when in standby, by the number of hours it is in standby per annum. Having established the likelihood of any improvements made regarding power reduction being a result of replacing appliances, efficiency here is seen to be more closely related to the age and quality of the appliance. This should be a key consideration when judging whether it's appropriate to replace an appliance or not, and when selecting new appliances. The general upkeep and frequency of use should also inform this decision. For example, a typical kettle boils water by heating an electric element that sits in the water, transferring the heat directly to the water. Usually, the user will boil more water than is required to make the drink or cook the food, and so energy is wasted heating unused water. This water will also usually cool before the next use. An example technology upgrade might be an instant boiling system that only boils what is required. The 4th generation Zip HydroTab B100 is an example. It can provide 100 cups of instant boiling water per hour. The auto shut-off function turns the system off after hours and on weekends, and it will also switch to the auto sleep mode when not being used. Also available are taps that can dispense chilled water or hot water. A cheaper, less permanent solution to replace a kettle is an instant kettle that heats the water as it is dispensed. Achieving energy efficiency in extraction. Hood fans are essentially purpose-specific extraction fans. Calculations regarding this can be found in Energy Session 5.0, Thermal Performance and Climate Control. It should be noted though that variable speed vents can save 30 to 50% on ventilation energy costs just by allowing you to increase your fan speed during busy hours and decrease during lull periods. Often you can retrofit your current system with variable speeds. You can also buy a system that automatically adjusts fan speeds based on demand. Side panels lower needed exhaust rates by reducing cross drafts and encouraging the vent to draw air from the front, containing the heat and fumes from your cooking equipment. Backshelf, passover, or eyebrow hoods need less energy to work than wall-mounted or island canopy hoods. However, proximity hoods are not adequate for appliances using solid fuel like wood or charcoal. The next best thing is a wall-mounted canopy hood. An example scenario. An office kitchen promotes healthy eating practices for their staff and encourages the use of their kitchen facilities. The kitchenette area of the office has a new 4-burner electric hot plate. The 2 larger plates are 2 kilowatt each, and the remaining plates are 1 kilowatt. A quick search of the model number tells you that standby power is 1.25 watts. On average, the staff use the 2 larger hot plates for about 80 minutes each day, 5 days of operation per week, over 48 weeks of the year. Estimate the total energy use of the stove annually, and the total cost that it represents to the business if the business operates on Tariff 20, General Business Use, at 23.19 cents per kilowatt hour. To calculate the most accurate energy use, and therefore cost, we must account for standby energy use in using the following formula. Kilowatt hours per annum is equal to the rated power multiplied by the hours of active use per annum, plus the standby power multiplied by the hours of standby use per annum. To determine the energy used by the hot plates, we substitute in the rated power of the hot plates, which we know to be 2 kilowatts, multiplied by 2 hot plates. The time of active use of 80 minutes, or 1.333 hours per day, 5 days per week, 48 weeks per year, is also inserted. This gives us a total active energy consumption of 1,279.97 kilowatt hours per annum. To calculate energy use in standby mode, we enter the rated standby power 0.00125 kilowatts multiplied by the total hours of annual standby, calculated in 3 separate parts. The first calculates the standby used for the remainder of the day when the office is occupied, subtracting the active hours from 24 hours. The second part accounts for full weekend days of standby in the 48 occupied weeks. And the third portion calculates the standby power used for the full weeks per year the office is not occupied. This equals 8,416 hours of standby per annum and amounts to an additional 10.52 kilowatt hours per annum. Total energy use is then just the sum of the total energy use of the hot plates and the total energy use while in standby per annum, or a total of 1,290.49 kilowatt hours per annum. The cost incurred by the client is then the total annual energy use, multiplied by the cost per unit energy. This is equal to $299.26 per annum. To continue with presentations, please select Energy Session 10.0, Equipment and Entertainment from the navigation bar. To complete the assessment for this presentation, please select Tutorial 9.0, Food Preparation.